for the past 5 years, I would say 5+ years, I've been interested in the impact of astronomy on climate change. As Alberto mentioned, I was living in Hawaii and working in Hawaii for about 6-7 years, and that's where it started. There was the TMT protest, the 30-meter telescope protest in 2015, that in my mind started all of this reflection about the place of astronomy in the world. Are we the good guys, or are we not? Is there something we can do better in our culture? And in particular, I started to look into the climate footprint, right? There are many other aspects that I could talk about, but in this presentation, I will just focus on climate change. But there's a whole aspect of sustainability, diversity, equity, inclusion. All those aspects basically came to the front of my head in those years. And I started to add those aspects in my work, even though I'm not paid for that, right? We are paid to develop a new telescope and to write papers, but I thought it was very important to dedicate some of my time to this sort of effort. And as Alberto surely said, I'm an astronomer. I'm not a climate scientist. I read books, I read papers, mostly published by our community, so astronomers, but I also read books published by other people. And so I'm going to give you some information about what I gather, and hopefully that's accurate enough and helpful enough for all of us to think about what can we do, what should we do as part of the astronomy community to do something about climate change. So usually I'm not using, okay, cool. So briefly, I'm going to talk a little bit about climate change in general, and then I'm going to talk about our footprint. And hopefully that will lead us to some questions about, okay, what can we do? What are the solutions? But beyond that, there's another question that we need to ask ourselves is, are we ready to implement those solutions? It's one thing to know them, it's another thing to actually implement them. Oh, that's not going to work. I have the PDF version of my talk. This should be a movie, but that's fine. Climate change, I'm pretty sure all of us in the room here online, we know climate change is real. It's caused by humans. And it's a crisis of the present, not only of the future. On the side here, the movie is supposed to show temperature, average temperature on the planet since 1880. So almost 150 years of data collected by NASA. And that shows that up until the mid 20th century, the temperature is roughly around that 0 degree increase of temperature with respect to the pre-industrial era. And then as you go to the 1950s, 60s, 70s, 80s, up to now, the temperature slowly but surely increases. And I'm sorry that I converted my talk to PDF so you can't see the plot, but I encourage you to look for that very nice spinning temperature. And basically, as we reach the 2000s and the 2010 and 2020s, the temperature keeps rising until it reaches at least +1 degree compared to pre-industrial era and up to maybe 1.5 this year. So we know those data, right? They exist there. We know that the temperature is rising. And so before I go into more of the science behind it, I sent that survey, and I don't know who actually answered it. I think it was mostly students, but there is that study that is made by a program at Yale on the climate change perception of American, but that's their main study. But recently they released more information about the world. And they defined those 6 categories of American from alarmed to dismissive. And in the survey, for those of you who took it, I described what those 6 categories are. Basically, the alarm is the has the strongest belief in global warming, the fact that it's caused by humans. They are very concerned by it, and they are motivated to do something about it. And on the other side of the spectrum, you have the other aspect. They don't really think that global warming is real or that it's caused by human beings. They are not concerned about it, and they don't want to do anything about it. And so I asked you all to say, okay, where do you think that most American people surrounding you, where do they land? And I'm going to show various results. So I asked that same question about a year ago. And you see, hopefully this is not in the way. You see that when I asked that question a year ago to about 40 astronomers that attended a meeting, most people thought that, okay, on average, the people around me might be cautious, maybe disengaged, maybe concerned, but they are kind of in the middle. I asked again, I presented those slides just a week ago to colleagues here at Space Telescope, and those were their answers. Very similar, in fact, a little bit more skewed to disengage, but you see again, the mass of the people think that the average American is cautious or disengaged. It's not on one side, it's not on the other side, it's kind of in between. And so I asked you the same, and I think I got 13 answers, very similar again. So the sample is a little bit smaller here, so no one said alarm, no one said dismissive, but again, everybody said somewhere in between, maybe a little bit toward disengaged. So you see that those three surveys, it's not statistically representative, but it's in our field, it's astronomers over a couple of years, all give kind of the same answer. This is the real answer. So when you do the survey online, so of the Yale program, they do the survey in a professional way. This is what they get. So this is what you thought, this is what's reality. And that's the first point that I want to make, is that we have the tendency to believe that half of the population in the US or in the world think that climate change is real and it's concerning, and the other half thinks that, oh no, it's not true. Because I think quite often when we see on TV or in newspaper, people talk about climate change, we have the climate scientist and the climate denier, making us believe that there is a 50-50 break in the world about how we think about climate change, but that's not true. It's a very biased way to show things. It's not 50-50. It's like 97% of the climate scientists are convinced that climate change is real and is caused by humans. So in truth, the people around us are convinced by more than 50, almost 60%, that they should be concerned and alarmed about climate change. So that's the first thing, is that how you perceive them and what they are is different. So we should be a bit more optimistic about how people around us think. And so recently I found, like just a couple of days ago, I found that same program from Yale, instead of just doing the US, did the whole world. And there are a couple of things here that are of interest. Is when you look on the left side, those are the top 15 greenhouse gas emitting countries based on the available data that they have, excluding China, Russia, and Iran. So you see from Mexico to the US to Germany to Indonesia. And in those countries that are, let's say, polluting the most, you still have a significant fraction of the population, 80 to 55%, who are concerned or alarmed about climate change. So even in polluting countries, and some of them might not be too much affected by climate change, like Germany, let's say, most of the population is concerned about climate change. And on the right, you see a focus on North America, Central America, and the Caribbean. And you can see that there is a place that is at the top there in terms of being alarmed by climate change, and that's Puerto Rico, with 88% of the people sampled who said they are alarmed or concerned. So there is a significant variation across the world, and Puerto Rico is among the top of the people being the most concerned by climate change. So now I asked also another question, which is, how concerned are you? So the plot that I showed before, the question that I asked you before was, how concerned do you think other people are? And I asked you how you are concerned. And again, I'm going to show you numbers from my colleagues from last week and from you. And you see that it's overwhelmingly alarmed when you ask astronomers. Nobody's in the bottom three categories. When I ask you, same thing, like 80% of you are alarmed and 20% are concerned, roughly. So that's something very important to have in mind, is how you perceived others and what is the reality, and what is the reality in our field of basically scientifically educated people. Those are very different things. And maybe you should be a bit more optimistic. We should all be a bit more optimistic about how other people around us think about climate change. If there is any question, feel free to interrupt me. I turn off my screen so I don't see you, but feel free to just interrupt. So now I'm going to give a very simplistic view of climate change and where it's coming from. So it starts with how much carbon you have in the atmosphere. There is a natural cycle, basically, of carbon on the planet between the plants, the animal, the soil, the ocean, the sediment deep into the ground, and the atmosphere. And that cycle, the natural cycle, is roughly at the equilibrium. In fact, it's pumping a little bit carbon from the atmosphere into the other storage location, about 4 or 5 gigaton per year. But now if you add the human contribution to it, so let's say call them non-natural, but human-caused perturbation, mostly you have fossil fuel burning, and that's about 8 gigaton per year. So instead of having a sink of about 4 or 5 gigaton per year, now you have a source of 4 or 5 gigaton per year. So we put 4 or 5 gigaton per year of carbon into the atmosphere. And the very simplistic way to see that is we are burning fossil fuel. It's in the name, it's fossil. It's supposed to be in the ground, and it takes a lot of time to go into the ground to turn into oil and gas and coal. But we're burning it at a rate that is much faster than the rate at which it's going back into the soil. And that creates a perturbation, and that increases the CO2 concentration in the atmosphere. So now we have a lot of CO2 in the atmosphere. What does it do? Well, it's the greenhouse effect. People in our field study it as well. Even though we are not climate scientists, we look into greenhouse effect because we look for extrasolar planets who might be habitable. And the greenhouse effect is very important to have liquid water. It plays a role. And when we look at our planet, we know that the concentration of CO2 in the atmosphere correlates very well with the temperature. It's not the only effect, it's not the only thing that drives the temperature, but it's one of the most important ones. And it's true over hundreds of thousands of years, and it's also true over the past century. So those two graphs show the clear correlation between the CO2 and the temperature on the planet. So we increase CO2 by burning fossil fuel, that increases the temperature. What happens when we increase the temperature on the planet? Well, a lot of things start to go wrong. It affects our water supply, our food production. It affects our health, not only physical, but mental. It moves people around. It increases flooding. So basically, it affects our infrastructure. That may affect the economy, and so on and so forth. A lot of consequences. I'm not going to spend too much time on this, but we know that there are measurable effects of the increase of temperature in the world. And when I gave that presentation a year ago, it was shortly after those very intense fires in Canada. And I think it was a week after. And during those days, there was a massive cloud of dust that came from Canada and that was covering New York City. It was visible also in Baltimore. There was a news that said that July 3rd had been the hottest day on Earth on record until July 4th, so the day after. There was intense flooding in the Northeast, like I think it was a few weeks before. So the news was really telling us the story. And when I gave the presentation last week, and I'm giving it to you now, you may wonder, okay, but since last year, has it gone better? And yes, the answer, of course, is no. You may have read about the news that the past 13 months since last June have been the hottest month on history, on record. So last June was the hottest June ever until June 2024. Last December was the hottest December ever. And now that has been the case for 13 months. And I think that, I don't remember exactly the number, but I think it's 5 or 6 of those months have been above 1.5 degree increase with respect to pre-industrial period. So we increase the concentration of carbon in the atmosphere, it increases the temperature, it triggers a lot of effects on the planet. So how do we respond to this? The answer is quite simple. We just need to reduce our carbon emission. Our CO2 emission needs to be reduced. But there is a delay between what you see on the left, which is the concentration of carbon, or on the right, sorry, on the carbon concentration in the atmosphere, and what are our emissions. It takes time for the atmosphere to handle this increase or this decrease of emission. And so you see that if we want to have an effect on the concentration of carbon in the atmosphere, we need to act very quickly. To see an effect tomorrow, we need to act yesterday. And we need to do it soon, we need to do it strong. So I'm going to go back to that central plot here that shows our emission year after year. So that's from I think that's from the IPCC report. Yeah, the sixth report of the IPCC, the Intergovernmental Panel on Climate Change. And you see the same curves, right? It's the same as what I show here, both in blue. The curves that tell us how much emission we are allowed to, if we want to limit the global warming to 1.5 degrees or to 2 degrees. And you see in orange, the NDCs, the nationally determined contributions. So what the various countries in the world have committed to. And instead, it's not enough. Right? We need to be bolder than that. It needs to be stronger than that. It needs to come faster. One note quickly on the side, and I'll try to make sure that you have access to the slides later, but as I was preparing this presentation, I realized that one issue is that units keep changing. On that plot, you have gigatons of CO2 equivalent emission. On other plots, you will have gigatons of carbons. On others, you're going to have gigatons of CO2, not CO2 equivalent. CO2 equivalent means you take into account methane, sulfur oxide, all the nitrous oxides, and all the other gases, and you convert them all in CO2 equivalent. And then you also have to take care of, do you take into account all the emissions or only some of them? So on my slides, and I'm not going to detail all the calculation here, but if you want to go back to them later, you can see the conversion between one unit and the other. So they are consistent. So we need to decrease our emissions quickly, strongly, yesterday. Now, how do we do that? How much? So one way to look at it is, imagine you have a big bucket that you fill with CO2. And the goal is to not overfill the bucket. Every year, the planet takes a little bit out of this bucket naturally. But we fill it very quickly. We put 40, 50, maybe even 60 gigatons per year of CO2 equivalent. Now, if we want to have a chance to reach 1.5 degree, and let's say we want to be very sure, we want to be at 83 degrees. And hopefully you can see my mouse moving here, but 83% chance of success. 83% chance of success to reach 1.5 degree. We have 100 gigatons left in the bucket. But we emit about 40 tons per year. That means we have 2.5 years left before we cut everything. If we go to 2 degrees, we say, okay, let's try not to meet 1.5 degrees, let's try to meet 2 degrees. We have 800 gigatons left. That's 20 years. The message, and that's 20 years and after zero. 1.5 degrees, that's 2.5 years, and then 0. The message here that I want, especially people who work in astronomy, to understand is the time scale. We're not talking about billions of years or millions of years. It's now, it's this generation that can act, that has to act. Those numbers are very small. And that's why the drop is very fast here. To have a chance to reach 1.5 degrees, we need to act quickly and very strongly. So now you may ask me, okay, what is the difference between 1.5 and 2 degrees? I mean, if we can have 20 years instead of 2, that'd be better. And so here I'm going to quote the General Secretary of the United Nations. He gave a speech earlier last month on World Environment Day. And this is just quotes from his speech. He was saying, why all this fuss about 1.5 degrees? It's because our planet is a mass of complex connected systems, and every fraction of a degree of global heating counts. The difference between 1.5 and 2 degrees could be the difference between extinction and survival for some small island states and coastal communities. It's the difference between minimizing climate chaos or crossing dangerous tipping points. 1.5 degrees is not a target, it is not a goal, it's a physical limit. And the way I read that, it's basically, when you see in the IPCC report 1.5 and 2 degrees, it's not because it's a round number and because it looks nice to just say 1.5. It's because there's a physical reason behind it. Above 1.5 degrees, there are something that we don't understand very well, how they will collapse and trigger other things, those tipping points. There will be an escalation of events if we reach 1.5 and we stay above 1.5 for too long. That's the reason behind it. There's really a physics behind it. So let's assume we want to meet 1.5 degrees. I want to give some numbers, so hopefully you have them in mind. So that's again from the IPCC report. You see the emissions from 2019 in the world, close to 60 gigatons of carbon, of CO2 equivalent per year. And the numbers that we should be at in 2030, 2035, 2040. Instead of giving them globally, I give them per person in red up there, per year per person. And you see that roughly right now we are at 7 tons per year per person. By 2030, which is only in 6 years, we want to be at almost half of this, 4 tons per year and per person. And by 2040, we want to be another half of that, so 2 tons. So let's keep that in mind as I go forward. One important thing to be aware of is, of course, those average number, they don't represent the world properly. Not everybody on the planet emits the same. And so there's a very interesting plot here from the International Energy Agency that shows emission per regions, but also per decile of income. So basically, as you see, let's say China is in orange here. Those are the 10% wealthiest people in China. This is the next 10%, the next 10%, et cetera, et cetera. So every region is cut like this in bucket of 10% by income. What you cannot see immediately from this plot is that if you were to take the 10% of the wealthiest person in the entire world, they are responsible for 48% of the emission, half of them. That's telling. On the other hand, if you look at this global average here, 4.7 tons of carbon, of CO2 per capita, 5.5 billion people are already below that number. And as I looked on that chart online, I found out that 4.5 billion people already emit less than that number of 4 tons of equivalent per person by 2030. So you have 4.5 billion people who are already meeting the goal. Are we going to ask them to make an effort to reduce even more their carbon footprint, or are we going to ask the people at the top here to reduce their carbon footprint? I would even argue that the people who are really down there, they may ask to be able to increase their carbon footprint to develop their country, their lives, to have access to more resources than they have right now because they have access to almost nothing. So there is a very important discussion to have here about who will contribute to the reduction? And as you keep that question in mind, I want now to transition to us. Where are we on those charts? Is the research in astronomy sustainable? What do we know about the typical carbon footprint of an astronomer or a person working in astronomy? What is their professional carbon footprint? I'm not going to talk about what is mostly represented on those graphs here, which is life footprint, everything. I'm just going to talk here about the professional carbon footprint. What do we do for our work? And there have been quite a few papers now published about our carbon footprint, the carbon footprint of research, meetings, and entire communities. And the following slides, I'm going to show you some of those numbers. So I'm pretty sure that if I had asked you, what do you think is our main contribution, you would have said travel. And so some people looked at that first. It's like, what is the carbon footprint of attending a big meeting like the European Astronomical Society? Or more recently, this year, a paper that covers all the astronomy travel. And the numbers that are found at about 1.5 tons of carbon per participant, per individual. And so that's typically the carbon footprint of a flight between, let's say, the US and Europe, roughly. And so 1 ton is not too big, but if you think about it, it's already a very significant fraction of what we will be allowed to emit as human beings, not just as professional, but including our private life, by 2030, right? The limit is 4 tons. So it's already 25% here, or a bit more, that our professional travel is taking. By 2040, this will represent almost half, or maybe even more than half, of our carbon footprint that we are allowed to. So we will have to talk about travel. But that's not the main issue. So there have been plenty of other papers published. And again, I'm putting those numbers up there, those reference numbers. So I published a paper, the first paper that looked at the carbon footprint of a ground observatory. That's CFHT in Hawaii. And what I found was it was 17 tons of carbon per year per employee. There was a paper that looked at the entire Australian astronomy community, and they found it was close to 40 tons per year an employee. In the Netherlands, they also published a similar paper. They found it was much smaller, almost 5 tons, still above what we are allowed. But you see the difference between Australia and Netherlands, between communities, what I showed earlier, right? Not everyone is the same. There's a paper from Jürgen Nödelseller a couple of years ago that looked at the carbon footprint of our infrastructure, all of them, ground observatories, space observatories, and they found that it was about 37 tons per year per person working in astronomy. There's a paper looking at the largest astronomy research institute in France, almost 30 tons per year. And then the last paper looked at the carbon footprint of the Keck Observatory in Hawaii, following what I did a few years before. And they published a number per night, because it's an interesting unit, because astronomers compete for time on Keck, and they get nights or half nights. And by getting the number per night, you can see what is your impact. And it's significant. All of those numbers are gigantic compared to what we are allowed to. And so I don't like to make like very red slides, but I think it's an important message enough to put it like this in bold and red. Because that's the key message in my mind. It's conveyed information that our professional carbon footprint, it's about an order of magnitude larger than what it should be within the next 10 years. If we want to have a chance to maintain the temperature increase below 1.5 or maybe 2 degrees. So that means we have to reduce our carbon footprint by close to 90%. And we need to think about how we're going to do this. And so that's where I'm going to go now a bit more into what are the solutions? What can we do, right? And hopefully that will trigger some discussion for the end of the talk. So the first aspect is, what are the main contributors to our carbon footprint? Is it travel? Well, the answer is it depends highly on the institute. In fact, it also depends on the scope that was covered by the GHGI, the greenhouse gas inventory, the listing of the carbon footprint. Not all those papers use the same method. They may not have covered all the same things. but still there are some trends. So the paper about the Australian community found that their main contributors was the use of supercomputers. It seems to be a thing in Australia. They use a lot of supercomputers. They were able to track the carbon footprint, and that was the main contributor. The two ground-based facilities in Hawaii, CVHC and Keck, the main thing was the use of electricity to operate the telescope at the summit. Those are very big machines. They use a lot of electricity. And even though in Hawaii, the grid, the electricity grid is cleaner than in the rest of the US, it's still a lot of emission. That astronomy lab in France, they did a very thorough analysis, and what they found was that it's collecting data from space. So they were able to track their contribution from, let's say, James Webb, HSC, and the other space telescope, and they claimed that that was their main footprint. So it was not something that they did in their lab. It's not a travel or anything they were doing in their lab. It was the fact that they were collecting data from a space telescope that they are partly responsible for, like all of us who use those data. In average, if you look at all the research labs in France, huge scatter, but what they found is that the main one typically had been the purchase of goods and services, purchasing food, laptops, whatever, you name it. That was the main thing on average across all research field in France. And then just last week, I asked my colleagues here, okay, at Space Telescope, what is it? Well, we don't know. Now, another point that I want to make is, so it's highly dependent on the institute, but it's also highly dependent on the individual. Not all of us in a given institute have the same carbon footprint. Students don't have the same carbon footprint as postdocs, who don't have the same carbon footprint as admin, who don't have the same carbon footprint as professors. And there was a very nice study made in France across discipline. 7,000 individuals responded to a survey, and what they found in this analysis was that the carbon footprint was highly correlated with visibility, scientific visibility. So basically, number of publications, number of citations, and things like this. So basically, the more visible you are, and that's kind of instinctual, right? It's like if you travel a lot, that's because you're visible or because you want to be visible. If you publish a lot, you might be invited more to conferences and things like this. Therefore, your carbon footprint is going to increase. So there's a correlation. The causation is not clear. What is the chicken? What is the egg here? But we see that again, like in the world, we are not all equal when we face carbon footprint. Now, my main message here is when you look at all of this, all the levers on which we can play, use of supercomputer, use of a summit facility, use of data from space, everything that we purchase, our visibility in science, all of this is actually what defines our field, our job, right? Our job is to do research, to use data, to publish it, to use supercomputers to reduce data, to purchase stuff, to build instruments, and then to travel to present our results. And all of those are important contributors one way or another to our carbon footprint. And therefore, my message here is that if we want to reduce our carbon footprint, we will have to address our culture. We will have to redefine what it means to be an astronomer. And hopefully that will trigger some maybe discussion. Another point that I want to throw out there for you to discuss is, okay, should we actually do something? We are, what, a few thousand astronomers in the world? Maybe 10,000? I don't know the number exactly, but it's not much. So our carbon footprint is a very teeny tiny fraction of the world emission. So if we were to decrease our carbon footprint, what would it do? It would nothing, right? Yeah, it's true, it would do nothing if we were the only one. But what if everyone were thinking that way? Like if everyone on the planet say, oh, my individual carbon footprint is nothing, therefore I don't have to do anything. Then the consequence is that nobody will ever do anything and we will stick the way we are. We'll continue with business as usual, and that's not the right way to proceed. It's all hands on deck. It's all of us can contribute one way or another, especially those who emit the most. And that's my second point, is that on average, and if you look in detail, some of us emit a lot. I remember the year before I published my paper on this in 2019, I traveled quite a lot, from Hawaii to Australia to France to the continental US. And my carbon footprint was horrible. It was 19 tons of carbon just for flying. And I stopped flying after that. I was like, no, I can't do this anymore. I'm responsible for this and I have to show the example. And I think as scientists, when we follow the data, when we follow the knowledge, we can't hide behind it. And we can't say that it's the others who should do it when we are the one emitting more. And that's an issue in our field and beyond. There is that feeling. There are a couple of papers here that I hope that you will have a time to look at. One of them is titled "Concerned Yet Polluting." It relates to what I was showing to you at the very beginning of this talk. It's like most of us are concerned or very concerned about climate change, right? 80% in the top bill. In that analysis was 70%. 80% strongly or somewhat agree to calls for profound change in research practices. It's like, yeah, we want to change our research practices because we understand that something is wrong about it. But when it's time to ask about implementing those changes, it becomes difficult. I'm giving a quote here in the middle of the page that I heard from one of my colleagues at the top of the food chain, or close to the top of the food chain, I should say, who told me, but I don't want to give away my platinum status on airline, whatever it was, American Airline or something. It's like, we know there is an issue with climate change, but we want our little things, little gifts and toys. That doesn't make sense. And that's very well explained that second paper from Thierry et al. In 2023. It's more of an opinion piece, but it's very well documented that says, basically, there is no research on a dead planet. We have to do something if we want to preserve the goal of our culture. The goal of research is to train students, write paper, develop technologies, and answer questions. But if there is no future where this matters, what's the point of continuing to do research the same way, continuing business as usual? Because we are contributing to the collapse of the conditions that are required for us to continue our job. It's a self-fulfilling vicious circle, basically, and we need to get out of it. On that point, I wanted to show you now answers to some of the questions that I asked you about exactly that. And I'm going to show you also the answer from my colleagues from last week. So the first question was, do you think we should change our lives? And so those are the numbers before the slash here for Space Telescope and for you here. And you see it's very skewed toward the top, like you strongly agree or somewhat agree that, yes, we should change our life profoundly if we want to address climate change. But when I ask immediately after the same question about our profession, you see how the numbers drift down. It's not, we don't agree as much to change our profession as much as we want to change our lives. And that's true also from you. It's like some of you strongly disagree. There is a more balanced feel about our profession. And my hope is that after showing you some of the numbers here, you may reconsider and see that our carbon footprint as professional is very large, and that needs to be addressed. And so another question that went along the same line was the US average citizen basically should decrease their carbon footprint by about 70%, I think. And I ask you, do you think the US astronomy community should do the same, more or less? And Space Telescope colleagues and you are kind of balanced again. We should do about the same as everybody else. Even though now the numbers that I showed you say that we are at the top, we are among the biggest polluters, and maybe my opinion is that we should do more than the average person. And so I have just 2 slides, so I think I'm going to be done in a couple of minutes. Last week, when I asked those questions to my colleagues, and you can take it and reframe it for you, I was asking, okay, what is it about us? Space Telescope Science Institute, we operate space telescopes. And again, those 2 sentences in quotes are actual quotes from people in the STSCI and NASA environment. And people tell me, well, it's not like we operate large ground-based facilities like NOIR Lab or ESO. our main impact is primarily travel. Well, it's not, as I just showed. The carbon footprint of space telescope is huge. And when people say, I believe the carbon footprint of space telescope is 0, is it? It's not. A space telescope in space, of course, does not do anything. It's in space there. It doesn't burn anything. But how did it get up there? Not by itself. It went on a rocket. It was built. A lot of people travel around the world to build that telescope. So the carbon footprint of a space telescope is definitely not 0. In fact, some papers try to evaluate this, and they show like the numbers are really large. Like it's in the tens of thousands of tons of carbon per year. And they try to normalize it per paper and per author. So you can compare it to those numbers that I gave earlier, the 7, 4, and 2. And you see again how this is a factor of a few at least larger. So the main thing here is we have an issue because we haven't measured our carbon footprint very well ever, especially at Space Telescope, because we are dominated by space missions, and those are based on extrapolation. They are not very clearly defined numbers. And my last slide that I sent as kind of a provocative question to my colleagues, and maybe you can feel the same about it, is we are now starting to work on the next very big space mission, Habitable Worlds Observatory. And I think it's very interesting because that mission is supposed to look for habitable worlds. And I wanted my colleagues and you to think about the context in which we will design, build, and operate that space telescope. It's going to be in the 2030s and 2040s, when the world will hopefully have changed. If in option 1, it hasn't changed, we have continued business as usual, and the temperature continues rising, and we are 1.5, 2 degrees already, and we're on the path to 3 degrees or more, I claim that no one will really care about astronomy anymore, especially about a mission that looks for a habitable world that is light years away. There's no planet B, in a way. And so if the world hasn't changed, I don't think anybody will care about HWO. Now, I hope that the world has changed and that we are on course to meet 1.5 or 2 degree global warming and not more. And so everybody around us in society, in the world, has decided to slow down and preserve our resources, preserve the social and planetary boundaries. What will we do when we build, design HW? Are we going to continue business as usual? Or are we going to do like everybody else? Are we going to start to be accountable in terms of environmental and social justice? Are we going to try to be sustainable? And that's where I will stop. I hope that those 2 slides will trigger some discussion, some questions, and I thank you very much for your time and for the invitation. Thank you.